What would Saturn be without its rings? These imposing rings make Saturn one of the most fascinating planets in our solar system, and certainly the most beautiful. They are its signature, its identity. But have they always been there? And above all, will they always exist? What if I told you they might be younger than the dinosaurs, and that their disappearance has already begun right before our eyes, slowly but inexorably? But Saturn is not just a simple ball of gas, surrounded by spectacular rings. Over 1 billion kilometers, or 621 million miles away from us, Saturn is almost inaccessible. And yet, thanks to our probes and telescopes, we are gradually uncovering some of its secrets. Its poles hide geometric storms with impossible shapes. Its moons, stranger still, defy logic. Oceans beneath Enceladus's ice. Liquid methane rivers on Titan. Dear traveler, greetings. Today we go beyond the limits of our world. We will delve into the depths of Saturn, explore its icy moons, and try to understand what makes this planet such a unique place. But before embarking on this extraordinary adventure, take a moment to support this expedition. Like this video and subscribe to the channel to not miss any of the upcoming explorations. Thank you, and get ready. The journey to Saturn begins now. You will probably never have the chance to see Saturn from space, but we will witness a rare astronomical phenomenon in early 2025. On March 23, 2025, the famous rings of Saturn disappeared, at least in appearance. On this day, Saturn was aligned in such a way that its rings were perfectly edge-on relative to Earth. And since their thickness is incredibly thin, barely a few dozen meters or 33 feet on average, they became almost invisible from our telescopes, a fascinating phenomenon that occurs only every 15 years. But why such alignment? It is a direct consequence of Saturn's tilt on its orbit. Just like Earth, the planet with rings tilts slightly over the years, changing the angle under which we observe them. Sometimes widely open, sometimes almost imperceptible, the rings offer a spectacle in perpetual evolution. Without the brightness of the rings, it becomes easier to observe some of Saturn's discrete moons, usually drowned in their glow. And then, we will have to wait until 2032 to, on the contrary, observe Saturn's rings from their most spectacular angle. In that year, the planet will reach the maximum tilt of its rings. Unlike 2025, they will open before us at 27 degrees, offering a view of exceptional precision. Thanks to this maximum tilt, we will be able to admire their underside, usually hidden, and observe details invisible under normal circumstances. This configuration will also offer optimal brightness, and Saturn will then present itself as a giant adorned in its most beautiful crown. And you better take advantage of those exceptional moments, for as majestic as they are, Saturn's rings are not eternal. Their glow, which has fascinated astronomers for centuries, is fated to disappear. But rest assured, it will take millions of years before Saturn becomes a naked planet. Nonetheless, this disappearance process is already underway before our eyes. But then, what exactly is happening? The phenomenon responsible for this gradual disappearance is what scientists call ring rain. Contrary to what one might think, the rings are not solid. They consist of billions of ice and dust particles in perpetual motion around the planet. Under the effect of Saturn's gravitational forces and its magnetic field, these particles are gradually attracted towards the planet's atmosphere. Once captured, they slowly fall in the form of icy micrometeors, a phenomenon one could literally compare to a fine cosmic rain falling on Saturn. Recent observations from the Cassini probe have confirmed that this ring rain causes Saturn to lose several tons of material per second. At this rate, scientists estimate that the rings could completely disappear in 100 to 300 million years, a duration that seems infinite to us, but which, on a cosmic scale, is incredibly fast. But let's return to the composition of Saturn's rings. What do we really know? When we observe Saturn, its rings appear to form a continuous and uniform structure. However, this appearance is deceptive. The rings are neither solid nor homogeneous, but composed of billions of individual particles moving around the planet. For a long time, their nature was a mystery. The first observations of Saturn through a telescope raised far more questions than they provided answers. In 1655, the Dutch astronomer Cassini-Huygens made a major leap by discovering that Saturn was surrounded by a single ring. He understood that this structure was not a protrusion from the planet, but a distinct disk. That same year, he also discovered Titan, Saturn's largest natural satellite. A decade later, in 1675, another astronomer, Jean-Dominique Cassini, revealed an even more fascinating detail. This ring was not singular, but actually composed of several distinct concentric rings. He notably observed a wide separation between two rings, which today bears his name, the Cassini division, which separates rings A and B. At that time, only two main rings were known, A and B. But scientific advances have revealed that Saturn's ring system is much larger and more complex than it appeared. In reality, it is composed of 7 main rings, discovered gradually and named in an order that doesn't correspond to their position. The closest to the planet are the D and C rings, more tenuous and diffuse structures, difficult to see from Earth. Further out, the B ring, one of the brightest and densest, stands out for its strong reflection of sunlight. It is separated from the A ring by the Cassini division, a wide, dark band, revealed since the 17th century, as we have just seen. The A ring, although less opaque than B, remains impressive and is one of the most marked structures of the system. Beyond this main area, other formations intrigue astronomers. The F ring, particularly narrow and dynamic, seems in perpetual motion, influenced by the gravitational interaction of small nearby moons. More diffuse still, the G ring stands out for its low density, making it more challenging to observe. Finally, the E ring, the outermost, extends over a vast distance, up to 300,000 kilometers or 186,000 miles, and owes its existence to geysers from Enceladus. But this architecture is not limited to these 7 major rings. What was perceived as distinct bands actually hides a much more detailed structure made of a multitude of interwoven ringlets. Today, it is estimated that there are nearly 1,000 of these, forming a complex system where each particle follows its own orbit, influenced by the gravity of Saturn and its moons. Their composition also explains their striking brightness. Composed of more than 95% pure water ice, these rings reflect sunlight with an intensity that gives them this brilliant and ethereal appearance. But they are not made only of ice. They also contain dust, rocky fragments, and other materials, whose exact nature varies greatly from one ring to another. Their size varies considerably. Some particles are as small as a grain of dust, while others reach several meters or over 10 feet in diameter. At this scale, these rings are not simple disks floating around Saturn. They are alive, evolving, constantly sculpted by gravity, collisions, and the complex interactions that occur on a cosmic scale. Despite centuries of observation and study, the origin of Saturn's rings remains an unresolved mystery. How could such a structure have formed? Have they always surrounded the planet, or are they the result of a more recent cosmic event? 2 major theories currently compete to explain their appearance. The first hypothesis suggests that the rings are the remnants of an ancient moon of Saturn that ventured too close to the planet. Under the effect of extreme gravitational forces, this hypothetical moon would have crossed the Roche limit, a zone beyond which the planet's attraction is so powerful that it prevents a celestial body from remaining intact. Trapped in this fateful zone, the moon would have been slowly disintegrated, its fragments gradually stretching into a dense and spectacular ring. This theory would explain why the rings are primarily composed of ice, as this moon could have been an icy body similar to Enceladus or Titan. Another theory argues that the rings are the remnants of a titanic collision between two moons. In this hypothesis, two icy satellites of Saturn would have engaged in a deadly gravitational dance, eventually colliding at high speed. The impact would have shattered these moons into pieces, ejecting billions of fragments into space. The largest pieces would have fallen onto Saturn or been ejected, while the smaller ones would have settled into orbit, gradually forming the rings we know today. This explanation would also help interpret the diversity of particles present in the rings. Although they are mainly composed of ice, they also contain traces of rocks and various materials, suggesting a complex and violent origin. So, which of these theories is correct? Scientists continue to study the evolution and dynamics of the rings to try to answer this question. But another great mystery concerning these rings is the question of their age. Some studies suggest that they could be relatively young, formed only 100 to 200 million years ago. Only a future space mission, capable of analyzing in detail the composition of the rings and precisely dating their particles, will be able to settle this fascinating debate. In the meantime, they remain one of the greatest cosmic spectacles. But if Saturn's rings certainly fascinate us the most, what do we know about this incredible planet? Saturn is the second largest planet in the solar system. With a diameter of about 120,000 kilometers, or 74,565 miles, Saturn could contain more than 760 Earths in volume. It is so massive that it ranks just behind Jupiter, its impressive neighbor, and vastly dominates all the other planets in the solar system. But despite this colossal size, Saturn is surprisingly light. Like Jupiter, Uranus, and Neptune, Saturn is one of the giant planets mainly composed of gas. It is composed of more than 96% hydrogen and about 3% helium, with some traces of methane and ammonia. This makes its density extremely low, so much so that if you could immerse it in a giant ocean, it would float. No other planet in the solar system has such a strange feature. But that's not the only peculiarity that sets it apart. Saturn is also a planet that spins at a dizzying speed. It completes a full rotation on its axis in only 10 hours and 34 minutes, an impressive feat for a celestial body of this size. This rapid movement has a spectacular effect. It flattens the planet at its poles and gives it a slightly oblong shape. This flattening is the most pronounced of any planets in the solar system. But while its rotation is incredibly fast, its journey around the Sun is much slower. Located 1.4 billion kilometers or 869 million miles from the Sun, well beyond the asteroid belt, Saturn occupies the 6th position in the solar system. This distance represents nearly 10 times the Earth-Sun distance, and Saturn takes 29 Earth years to complete a single revolution around its star. Such a distance has direct consequences on its climatic conditions. The sunlight there is 100 times weaker than on Earth, and temperatures average around 180 degrees or 292 degrees Celsius. Its climate, although dominated by icy temperatures, is influenced by a rotation axis tilted at 27 degrees, similar to that of Earth. As a result, Saturn experiences very marked seasons, but these last much longer, nearly 7.5 years each. The atmosphere, thick and tumultuous, is swept by violent winds and titanic storms. Diving into this atmosphere, one discovers a layering of gaseous strata, each with its own characteristics. An upper layer, composed of ammonia clouds, where the temperature drops to 250 degrees Celsius or 418 degrees Celsius. An intermediate layer, rich in ammonium hydrosulfide, where it is about 70 degrees Celsius or 90 degrees Celsius. A lower layer, where the pressure is so extreme that the temperature can rise to plus 160 degrees or 140 degrees. In this world of gas and furious winds, Saturn also experiences spectacular phenomena similar to those found on Earth, such as northern and southern auroras. These dancing lights appear at the planet's poles, created by the interaction of the solar wind with its powerful magnetic field. But on Saturn, these auroras take on much larger and brighter dimensions, illuminating the atmosphere with incredible intensity. Among the many strange phenomena that shape Saturn's atmosphere, the hexagon at the North Pole is undoubtedly one of the most fascinating. This cloud structure, with its astonishingly regular contours, has intrigued scientists since its discovery. Why does a cyclone take a perfect geometric shape? Why has this structure persisted for decades, while storms on other planets like Jupiter constantly change? This atmospheric hexagon, whose contours are drawn by swirling winds, extends about 30,000 kilometers or 18,641 miles wide, 4 times the size of Earth. Each of its sides measures nearly 13,800 kilometers or 8,578 miles, forming a perfectly regular polygon. But it's not just a simple shape visible on the surface. The hexagon is a three-dimensional structure made up of several hazy layers that extend between 7 and 18 kilometers or 4 to 11 miles in thickness. At its center, a huge vortex roars with winds exceeding 500 km/h or 311 mph. And at the hexagon's borders, powerful jet streams form its contours, creating the stable and strange shape that defies the classical laws of meteorology. And it is this stability that intrigues the most. While terrestrial or Jovian storms evolve and dissipate, Saturn's hexagon maintains its shape and size for decades, despite the planet's rapid rotation and atmospheric turbulence. Its origin remains a scientific mystery. A hypothesis advanced by researchers is that the variations in speed between Saturn's different atmospheric winds create this natural geometric pattern. This kind of structure can be reproduced in laboratories and rotating fluids, but Saturn's titanic scale leaves many questions open. Another curious fact: this phenomenon is unique. No other planet in the solar system has a comparable meteorological formation. Even at Saturn's south pole, a huge vortex exists, but with no sign of a hexagon. Why such asymmetry? What keeps this shape stable over the years? Saturn's hexagon remains one of the greatest atmospheric enigmas of the solar system. As you've understood, Saturn's atmosphere is far from peaceful. The winds on Saturn are among the fastest in the solar system. Near the equator, they can reach 1,800 km/h or 118 km/h, 3 times faster than the most powerful winds ever recorded on Earth. This incredible speed is due to the planet's ultra-rapid rotation and the fluid structure of its atmosphere. But what makes these winds even more impressive is their distribution according to latitude. Unlike Earth, where prevailing winds globally blow in the same direction depending on the regions, Saturn's winds alternate between east and west based on latitude. Beyond 35 degrees latitude north and south, this variation creates zones of extreme turbulence that fuel some of the planet's largest storms. If Jupiter has its famous Great Red Spot, Saturn boasts its own mythical storm, the Great White Spot. This spectacular phenomenon occurs roughly every 30 years, when an immense storm suddenly erupts in the planet's northern hemisphere. But unlike Jupiter's Great Red Spot, which seems permanent, Saturn's Great White Spot is a temporary phenomenon that is born, grows, and eventually dissipates. Yet, its magnitude is colossal. When it erupts, the Great White Spot can stretch over tens of thousands of kilometers or thousands of miles, sometimes engulfing almost the entire northern hemisphere of the planet. It doesn't vanish in just a few days. These titanic storms can last for months, even years, before gradually breaking down into smaller formations. But what makes this phenomenon even more spectacular is the intensity of its electrical activity. Its lightning, with a power 10,000 times greater than those observed on Earth, tears through the atmosphere with unimaginable force. At its peak, the storm can produce up to 10 lightning strikes per second, illuminating the planet like a gigantic interstellar storm, visible even from space. And these storms are not just simple weather disturbances. They profoundly alter Saturn's atmosphere over periods extending up to several centuries. Scientists have discovered that Saturnian storms leave traces long after their disappearance. By analyzing the deeper layers of the planet, they detected traces of ammonia, evidence that some of these storms have penetrated well beyond the visible layer. Furthermore, they modify the temperature, alter the chemical composition, and profoundly reshape Saturn's meteorological dynamics. And, in addition to these local transformations, they contribute to maintaining the planet's thermal equilibrium, redistributing heat and influencing its climate in the long term. If the storms and supersonic winds shape Saturn's atmosphere, the planet's influence doesn't stop at its tumultuous clouds. Its magnetic field, invisible but powerful, plays a key role in the surrounding environment. Gas giants are known to possess intense magnetic fields, and Saturn is no exception. But it stands out due to several intriguing characteristics. Unlike Jupiter's, which is tilted by about 10 degrees from its rotational axis, Saturn's magnetic field is almost perfectly aligned with its axis. This peculiarity challenges some theories on the formation of planetary magnetic fields, as such precise alignment is unusual and difficult to explain. Although this magnetic field is 700 times more powerful than Earth's, it remains significantly weaker than Jupiter's, whose strength vastly dominates the solar system. However, this does not mean it is without consequence. It generates an immense magnetosphere, an invisible bubble that shields Saturn from the charged particles emitted by the Sun. This magnetosphere interacts with the solar wind and traps energetic particles, creating a highly radioactive environment around the planet. The impact of this magnetic field extends beyond Saturn itself. It is indeed responsible for the spectacular polar auroras visible at Saturn's poles, as previously mentioned. But this magnetic field also has effects that extend millions of kilometers or miles, profoundly influencing its system of moons and rings. Some of its moons, such as Enceladus and Titan, evolve directly within this magnetosphere and undergo its electromagnetic variations. With 145 confirmed moons, Saturn holds the record for the largest number of natural satellites in the solar system. And these moons are not all mere blocks of icy rock wandering through space. Some of them are true worlds in their own right, with atmospheres, underground oceans, and landscapes that defy imagination. While Saturn fascinates with its rings, its true treasure might lie elsewhere. Each of its 145 moons tells a unique story, and all of them, once again, show us the complexity and diversity of this immense celestial realm. The most impressive of all is Titan. Larger than the planet Mercury, it is the only moon in the solar system with a dense and complex atmosphere. Rhea, the second largest, has a diameter of 1,527 kilometers or 949 miles and appears covered with a thick layer of ice. Iapetus, slightly smaller with its 1,472 kilometers or 915 miles in diameter, intrigues with its two-faced appearance, one half as bright as snow, the other as dark as coal. Dione and Tethys, more modest, reveal surfaces marked by ancient fractures and craters that testify to a tumultuous past. And then there's Enceladus. This small, ice-covered body hides some surprises, and Mimas, and many more. So many different worlds with varied origins and evolutions. But how is this multitude of moons organized? To better understand the diversity of all these moons, astronomers classify them into two major categories: regular moons and irregular moons, depending on the nature of their orbits and their likely origin. Among all the moons of Saturn, 24 are considered regular. This means they follow a stable orbit around Saturn. Their trajectory is prograde, meaning they rotate in the same direction as the planet's rotation, and their orbit is slightly inclined compared to Saturn's equatorial plane, distinguishing them from moons with more chaotic paths. These moons are the largest and most massive in the Saturnian system. Titan, Rhea, Iapetus, Dione, Tethys, Enceladus, and Mimas are among them. Their stability suggests they formed at the same time as Saturn from the disk of gas and dust that surrounded the young planet more than 4 billion years ago. Their importance in the history of Saturn is such that their names are drawn from Greco-Roman mythology, specifically from the Titans and Titanides, the brothers and sisters of Cronus, the Greek equivalent of Saturn. In contrast, 121 moons are classified as irregular. Unlike regular moons, they did not follow the same formation process and seem to have been captured by Saturn's gravity after the formation of the planet. Their orbits are more chaotic than those of regular moons. They are often eccentric, meaning more elongated than circular, and they exhibit a strong inclination relative to Saturn's equatorial plane. Some even have a retrograde orbit, rotating in the opposite direction of the planet's rotation. These characteristics suggest that these moons were once asteroids or fragments of celestial objects that crossed Saturn's path before being trapped by its gravitational force. These irregular moons are grouped into 3 major families, based on their orbital characteristics and supposed origin. The Inuit group includes 5 moons: Igirak, Kivyuk, Palyak, Siernak, and Tarkek. All follow a prograde orbit and have names inspired by Inuit mythology. The Gallic group is composed of 4 moons: Albiorix, Bebion, Ariapus, and Tarvos. They too are in prograde orbit. Their names are drawn from Gallic mythology. And finally, the Nordic group. It's the largest of the 3 groups. It includes the majority of Saturn's irregular satellites. These moons evolve on retrograde orbits, indicating an external origin before their capture. They bear names inspired by Nordic mythology, except for Phoebe, which, although part of the group, is the only one with a name of Greek origin. Among all these moons, some hide many mysteries. Titan is undoubtedly the most intriguing of all. With a diameter of 5,150 kilometers, or 3,999 miles, it is larger than the planet Mercury. This makes it the second largest natural satellite in the solar system, after Ganymede, which orbits Jupiter. But what makes Titan unique is its dense atmosphere, an exceptional phenomenon among known moons. Its orange haze, composed mainly of 95% nitrogen and methane, is thicker than Earth's atmosphere and generates a pressure 1.5 times greater than that of our planet. Thanks to this atmosphere, Titan's surface is shielded from solar radiation, allowing the existence of dynamic geological and meteorological processes. Its landscape is equally astonishing. Titan's appearance is both alien and strangely familiar, but it is based on a totally different chemistry. Rivers, lakes, and seas of liquid methane snake across its surface, carving out a landscape reminiscent of Earth. But here, water is replaced by liquid hydrocarbons. With temperatures around 180 baros or 292 deg, water can only exist in a solid state, forming an icy crust. It is thus the liquid hydrocarbons, mainly methane and ethane, that fill the valleys and fuel a meteorological cycle similar to ours, with evaporation, condensation, and precipitation in the form of methane rain. While Titan captivates with its atmosphere and surface landscapes, its real secrets lie deep below. Beneath its icy crust, nearly 50 kilometers or 31 miles thick, an immense subterranean ocean may be hiding, and it could reach a depth of 250 kilometers or 155 miles. If this ocean can exist, it would be thanks to the presence of ammonia. By lowering the freezing point of ice, ammonia allows water to remain liquid, despite the moon's extreme temperatures. Observations by the Cassini probe, which studied Titan for over 10 years, provided solid evidence of an ocean beneath the surface. By measuring changes in the ground, scientists found that Titan's surface deformed by nearly 10 meters, or 33 feet, under the gravitational forces of Saturn. Such a phenomenon is impossible if the crust rests directly on a solid core. This means that between these two layers, something liquid allows these movements, confirming the presence of an ocean. Another clue comes from the radio waves captured from Titan. Analyses revealed that at a depth between 50 and 80 kilometers, or 31 and 50 miles, a conductive layer disturbs the electromagnetic signals. This property suggests that the subterranean ocean contains dissolved salts or ammonia, making the liquid more capable of conducting electricity. These elements strengthen the idea that Titan harbors a vast reservoir of water hidden beneath its icy surface. Titan seems, in any case, one of the most serious candidates for habitability in the solar system. If life exists elsewhere, it might be under the ice of this moon that we could find it. The Dragonfly mission, planned to explore Titan in the 2030s, might well provide us with answers. Another promising moon for the search for extraterrestrial life, Enceladus. With its modest diameter of 500 kilometers or 311 miles, it might go unnoticed compared to giants like Titan. Yet, Enceladus is anything but a dead moon. Unlike satellites covered with craters frozen for billions of years, its surface is in perpetual renewal. Enceladus continuously transforms under the effect of powerful internal forces. Immense faults and fractures streak its icy surface, evidence of continuous tectonic activity. Some fissures, over 200 kilometers or 124 miles long and a kilometer or 0.6 miles deep, appear like large frozen scars. And in some regions, the ice crust even seems to have been smoothed and remodeled recently, erasing old impact craters. But what causes this perpetual agitation? The explanation comes from Saturn itself. Just as the moon raises tides on Earth, the powerful gravity of Saturn constantly stretches and compresses Enceladus throughout its orbit. This continuous deformation creates fractures in the icy crust and generates heat beneath the surface. And beneath this layer of ice lies an ocean, of course. But not just any ocean, a vast reservoir of liquid water in contact with a rocky core. How do we know this? Thanks to observations from the Cassini probe, which revealed a spectacular phenomenon: geysers erupting above the South Pole. These immense plumes of water vapor are projected hundreds of kilometers into space, forming a thin atmosphere around the moon and even feeding Saturn's E-ring. These geysers follow a well-defined cycle. Every 32.9 hours, corresponding to a complete orbit of Enceladus around Saturn, the activity of the geysers intensifies due to tidal forces. It's as if the ocean is being rhythmically influenced by Saturn's gravitational pull, somewhat like Earth's tides. But what makes these geysers truly fascinating is neither their scale nor their regularity, but their composition. The Cassini probe, by repeatedly passing through these plumes, conducted detailed analyses and revealed a mix rich in elements essential to life. 98% of the ejection consists of water, but there is also hydrogen, methane, carbon dioxide, ammonia, and sodium salts. Even more astonishing, nanometric silica particles have been detected. This discovery suggests that the water comes from an ocean in contact with a rocky floor where hydrothermal reactions are occurring. But the most exciting discovery remains the presence of complex organic molecules, some of which are considered precursors to life. Among them, hydrogen cyanide, a key molecule in the formation of amino acids, the fundamental building blocks of life. This is why Enceladus intrigues scientists so much, as all the necessary ingredients for life are present: liquid water, a source of energy in the form of hydrothermal reactions, and complex organic molecules. Moreover, unlike Titan, where the surface conditions are hostile, Enceladus's subglacial environment offers a stable setting, sheltered from the radiation and extreme temperatures of space. It is impossible to talk about Saturn without mentioning Janus and Epimetheus, two moons so close that they seem to play a strange game of hide-and-seek around the planet. These two small moons, approximately 180 kilometers or 112 miles and 115 kilometers or 71 miles in diameter, respectively, share almost the same orbit, only 50 kilometers or 31 miles apart. Such proximity might suggest a risk of collision, yet this is not the case. Every 4 years, a fascinating phenomenon occurs. The two moons swap their orbital positions. The one on the lower, slightly faster orbit gradually catches up with the other, but instead of colliding, their gravitational interaction forces them to exchange places. The orbit of one becomes that of the other, and vice versa, in a celestial choreography of extreme precision. This orbital ballet is a unique case, illustrating the complexity of gravitational interactions in the Saturnian system. Scientists believe that Janus and Epimetheus may have originated from the same celestial body, which fragmented in the distant past. Their similarity in size and composition seems to support this hypothesis. In any case, studying them provides more insight into the mechanisms of moon capture and evolution around giant planets. A beautiful glimpse into the invisible forces that constantly shape our solar system. While Titan, Enceladus, and the twins Janus and Epimetheus are the most famous in the Saturnian system, they are far from the only ones that pique the curiosity of astronomers. Some of Saturn's moons possess characteristics so strange that they seem straight out of a science fiction novel. Enigmatic landscapes, chaotic rotations, unknown structures, these moons fascinate as much as they pose questions. And among them, Iapetus is perhaps the most visually bewildering. With a diameter of 1,470 kilometers, or 914 miles, it is the third largest moon of Saturn, behind Titan and Rhea. But it is not its size that intrigues astronomers. It is its unique appearance. Iapetus has a stunning feature. Half of its surface is almost as black as coal, while the other is a brilliant white. This clear division between its two hemispheres often earns it the nickname yin-yang moon. But how can one explain this phenomenon? Scientists have several hypotheses. One of the main theories is that Iapetus slowly accumulates dark dust from another Saturnian moon, Phoebe. Phoebe orbits much farther out than Iapetus, but its constant impacts with meteoroids eject fine dark particles into space which, attracted by Saturn's gravity, end up settling on Iapetus. Another hypothesis suggests that this dark color is due to an endogenous process, with material being ejected from the interior of Iapetus that deposits on its surface. Whatever the true explanation, Iapetus remains an enigma, with the origin of the color contrast not yet fully understood. But it is not the only mystery of this moon. Iapetus also possesses an immense equatorial ridge, a gigantic mountain structure that stretches over 1,300 kilometers, or 808 miles, with peaks reaching up to 20 kilometers, or 12 miles high. This relief gives Iapetus an appearance that evokes a giant walnut, and once again, its origin remains uncertain. Some researchers think it could be remnants of an ancient ring that collapsed onto the surface, while others suggest that internal movements may have caused this strange structure. Iapetus intrigues with its two-tone appearance, while Hyperion stands out for its chaotic, irregular shape. From afar, this moon resembles a giant sponge floating in space. With an average diameter of about 270 kilometers, or 168 miles, Hyperion is not spherical like most other moons. Its surface is pockmarked with deep craters, giving it a porous, almost spongy texture. But what makes Hyperion even more unique is its strange rotational behavior. For a long time, it was believed that this moon spun completely randomly, never adopting a stable orientation. Unlike other moons that maintain a predictable movement around their planet, Hyperion appeared to change its orientation unpredictably, like an unbalanced top. This idea of a totally chaotic rotation was supported by several observations and simulations. notably thanks to measurements taken by Voyager 2 during its flyby in 1981. Also, through photometric analyses performed from Earth and numerical models simulating its orbital behavior. Hyperion seemed to be a unique case in the entire solar system, a moon whose movement defied all known rules of celestial mechanics. But this view has been recently questioned. By comparing observations taken over more than 20 years apart, astronomers discovered that Hyperion spins faster than previously estimated. It completes more than 4 full rotations per orbit around Saturn. So there is indeed a regular cycle in its movement. Another surprising revelation: its rotation axis seems aligned with its longest axis. In other words, although its shape is irregular, Hyperion tends to always orient its most elongated part in a specific direction, which provides an unexpected stability. This behavior led researchers to suggest that Hyperion might be in a nutation orbit resonance state. But what is a nutation orbit resonance? This phenomenon occurs when the way an object spins on itself and the way it wobbles are influenced by its movement around its planet. This means that instead of spinning completely randomly, Hyperion's rotation is influenced by external forces that maintain some balance, although it is not immediately perceptible. In fact, even though Hyperion seems chaotic at first glance, gravitational interactions between it, Saturn, and Titan could actually stabilize its rotation over long periods. This discovery is further evidence that our understanding of the Saturnian system continues to evolve. What we thought was a unique case of absolute instability could actually be a complex mechanism of orbital stabilization that we are just beginning to understand. In addition to its fascinating movement, Hyperion also intrigues with its internal structure. Extremely light for its size, it has an abnormally low density. This low density indicates that it is probably composed of a mixture of ice and rock with vast internal cavities, which would explain why it seems to float in space. After Iapetus and Hyperion with their unique appearances, another moon catches the eye. Yes, it's hard not to notice Mimas, as its appearance evokes an icon of pop culture. With its massive Herschel crater, which covers nearly a third of its 396 kilometers or 246 miles diameter, Mimas uncannily resembles the Death Star from Star Wars. This gigantic crater, about 130 kilometers or 81 miles wide, was formed following a titanic impact that nearly shattered the moon into pieces. Scientists estimate that if the impact had been a bit more violent, Mimas would have literally disintegrated. But beyond its spectacular appearance, Mimas may hide a much greater secret. Recent observations have revealed the possible presence of an underground ocean beneath its icy surface. This is surprising because, until now, Mimas was considered an inactive, entirely frozen moon. Measurements taken by Cassini have shown that Mimas wobbles slightly as it orbits Saturn, a behavior that could indicate the presence of a liquid water layer beneath the crust. If this ocean exists, it would be located at a depth of 20 to 30 kilometers or 12 to 19 miles, and its formation would be relatively recent, dating back only 5 to 15 million years. This discovery makes Mimas a new potential candidate for habitability, although conditions are likely more extreme there than on Enceladus. But let's return to Phoebe, the only irregular moon of the northern group that bears a Greek name. And for good reason. It seems to come from another world. With a diameter of 213 kilometers, or 132 miles, Phoebe is the largest of Saturn's irregular moons, and it is very different from the planet's other satellites. Its surface is dark and rich in carbon, giving it a very different appearance from the typical icy moons of the Saturnian system. And, like those in its group, its orbit is retrograde. Thus, it orbits Saturn in the opposite direction of its rotation. This suggests that it did not form at the same time as Saturn, but was captured later. Analyses of its composition show that Phoebe resembles objects from the Kuiper Belt, that icy region located at the edge of the solar system, where Pluto and other distant worlds reside. It could, therefore, be a relic from the early ages of the solar system, a remnant from the era when giant planets were forming and attracting objects from other regions. If this hypothesis is correct, then Phoebe is much more than just a moon. It could be a witness to the origins of the solar system, a fragment of a much older world. If some moons preserve the memory of the origins of our solar system, others actively shape the very appearance of Saturn. These discrete moons, called shepherd moons, are nothing like giants such as Titan or enigmatic icy moons like Enceladus. They are small, often irregularly shaped, and yet, without them, the rings of Saturn wouldn't be what they are today. These rings, which we imagine as perfectly fixed structures, are actually in perpetual motion. Billions of ice and rock particles continually move within them, following the complex gravitational forces exerted on them. And this is where the shepherd moons come into play. These small sentinels orbit near the rings and exert a discrete but essential influence on them. Their gravity acts like an invisible net, preventing the particles from scattering into space. They maintain the rings in place, sculpt their contours, and ensure that the divisions between them remain clearly marked. Without them, the fragile balance of the rings would be disrupted, and Saturn would gradually lose its majestic appearance. Some of these moons, like Pan and Daphnis, act as true cosmic sculptors. They navigate directly within the rings themselves, creating actual corridors in the surrounding material. With each passage, they push particles along their path, carving and maintaining visible divisions, like the Encke gap and the Keeler gap. Daphnis, in particular, generates around it astonishing ripples, as if the ring were a liquid surface disturbed by its passage. Others, like Prometheus and Pandora, watch over the edges of the F-ring, one of the most dynamic rings in the Saturnian system. Under their influence, this ring constantly changes appearance, as if it had a life of its own. Sometimes, filaments of material seem to stretch and detach before being pulled back into place. Even Janus and Epimetheus influence the distribution of particles in certain rings. In this complex system, nothing escapes gravitational interactions. Yet, these shepherd moons have nothing exceptional about themselves. They have no atmosphere, no spectacular geysers, no intriguing landscapes like Titan or Iapetus. Their role is due only to their strategic position, in the right place, at the right time. They are the guardians of the rings. They maintain and preserve a fragile system that without them would eventually dissipate. And that's the magic of the Saturnian system. Every element, even the most seemingly insignificant, plays a fundamental role in the balance of this miniature universe. From giant moons to tiny shepherds, from imposing rings to ice particles floating in the void, everything is in motion. Everything interacts. But if we know all this today, it is thanks to another key player in this story, space exploration. For Saturn, as majestic as it may be when viewed from Earth, only truly revealed itself to us when we dared to approach it. From the first telescopic observations to the probes that traversed its system, each mission has lifted a corner of the veil on this extraordinary planet. Saturn is visible to the naked eye from Earth, and for millennia, it was just a bright spot among so many others. But everything changed in 1610, when Galileo, armed with his rudimentary astronomical telescope, turned his gaze toward it. What he saw left him perplexed. The image was blurry, imprecise, but Saturn appeared to him as a planet with strange extensions on either side. He first believed them to be two large moons attached to the planet. Then, when they temporarily disappeared in 1612 because of the alignment of the rings with our line of sight, he thought he had made a mistake. Saturn was decidedly a baffling mystery. It would take until 1655 for Cassini-Huygens, with a much more powerful telescope, to discover the true nature of the rings. He demonstrated that they formed a disk surrounding the planet without touching it, and at the same time, he identified Titan, its largest moon. A few years later, in 1675, Jean-Dominique Cassini would reveal an even more fascinating detail. This ring was not a single block, but was itself composed of several distinct rings, separated by a dark space, which today bears his name, the Cassini division. These initial observations were just a glimpse. There was so much left to understand. For centuries, astronomers would refine their studies, improving instruments, tracking the minutest visible details. But a limit persisted. Observing Saturn from Earth was not enough. To uncover its secrets, we had to get much closer. The first close exploration of Saturn began with Pioneer 11. Launched by NASA in 1973, this probe first flew by Jupiter in 1974, before continuing its journey to the ringed giant. On September 1, 1979, after 6 years of traveling, Pioneer 11 became the first human-made object to approach Saturn closely, passing just 21,000 kilometers or 13,049 miles from the planet. This historic flyby provided the very first close-up images of the rings in Saturn's atmosphere. At the time, the nature of the rings was still a topic of debate. Were they young or old, formed from a single block, or made up of multiple fragments? Pioneer 11 lifted an initial veil on these questions, confirming that these rings were composed of individual ice and rock particles, not a solid disk as once imagined. The probe also measured Saturn's temperature, revealing that its atmosphere was much colder than expected, with winds blowing at staggering speeds. But what left a lasting impression was the discovery of a new ring, the F ring, a thin, bright band located outside the main rings. This major discovery immediately raised other questions. How could such a narrow ring exist without dispersing? Only later would we understand that it is held in place by the gravitational influence of shepherd moons, notably Prometheus and Pandora. Pioneer 11 also measured Saturn's magnetic field for the first time, confirming that it was much less intense than Jupiter's, yet it still influenced its spatial environment and numerous moons. But this mission was only a first glimpse. Pioneer 11 paved the way, but its technology was still rudimentary. Its instruments had limited resolution, and its flyby was too swift to permit more than a few spot analyses. Less than 2 years after Pioneer 11's flyby, a new mission was set to revolutionize our understanding of the planet and its system. In fact, not just one, but 2 new missions. Voyager 1 and Voyager 2, launched just weeks apart in 1977, aimed to explore the outer planets of the solar system. Their goal? To reveal what neither telescopes nor Pioneer 11 could show us. On November 12, 1980, Voyager 1 reached the planet and sent back the most precise images ever obtained of its atmosphere, rings, and moons. The probe revealed a gigantic and perfectly symmetrical structure at the North Pole, a hexagon frozen in the clouds, a unique atmospheric formation in the solar system. It also measured ultra-fast winds, blowing at over 1,800 km/h or 1,118 m/h, and highlighted a temperature difference between the poles and the equator. Saturn's atmosphere was far more complex than imagined, but what captured all the attention was Titan, that mysterious moon which had intrigued for centuries. It was suspected that it might resemble early Earth, with a dense atmosphere and perhaps even oceans of hydrocarbons. And Voyager 1's instruments confirmed part of these hypotheses. Its atmosphere is indeed very thick, composed mainly of nitrogen and methane, with surface pressure greater than on Earth. But a problem immediately arose. This atmosphere is completely impermeable to visible light, impossible to see anything on its surface. Titan remained a mystery. Titan then became a top priority for space exploration. If this moon hides landscapes shaped by a meteorological cycle of liquid hydrocarbons, a way must be found to see through this haze. The data collected by Voyager 1 was not enough. A more advanced mission was required, capable of going beyond simple visible light images. But before such a project could be imagined, Saturn had more wonders to offer. Less than a year later, in August 1981, Voyager 2 entered the scene. Unlike its twin, it did not focus on Titan, but on Saturn's rings and moons. And there, discoveries abounded. What was thought to be simple, homogeneous disks turned out to be a tangle of waves, twists, and complex divisions. The rings were not fixed. They were constantly sculpted by invisible forces. Voyager 2 then confirmed the existence of shepherd moons. These small satellites, by interacting gravitationally with the rings, maintained their structure and prevented their dissipation. But another inexplicable phenomenon caught the scientists' attention: the spokes of Ring B. Vast, dark structures that appeared and disappeared without apparent explanation. Saturn's magnetic field might be responsible, but the mystery remained. The rings were not the only ones revealing secrets. Voyager 2 discovered 4 new moons, including Atlas, Prometheus, and Pandora. But above all, one moon attracted particular attention: Enceladus. Its strangely bright and smooth surface intrigued. Too few visible craters, as if something constantly erased traces of the past. A movement of ice, eruptions below the surface. At the time, astronomers only had hypotheses, but an idea began to emerge. Enceladus might hide internal activity, perhaps even a subsurface ocean. It would take Cassini to confirm this intuition. After the revelations of the Voyager probes, one certainty emerged. We were not done with Saturn. Too many questions remained unanswered. It was no longer enough to just fly over the planet. We needed to stay there, study it over the long term, and explore this fascinating world in depth. Thus was born Cassini-Huygens, one of the most ambitious space missions ever conceived. Launched in 1997, Cassini-Huygens is a joint mission between NASA and the European Space Agency. The goal: to study Saturn and its system for several years. Cassini, the main orbiter, is the largest probe ever sent to the outer planets. Weighing over 6 tons, or approximately 13,228 LEBs, it carries a dozen state-of-the-art scientific instruments capable of scrutinizing Saturn's atmosphere, its rings, its magnetic field, and its moons. Huygens, on the other hand, is a module specifically designed for Titan. Its role? To land on this enigmatic moon and transmit unprecedented data on its atmosphere and surface. To reach its destination, Cassini-Huygens must travel nearly 1.5 billion kilometers, or about 932 million miles, a journey that takes 7 years. It uses several gravitational assists, bypassing near Venus, Earth, and Jupiter to gain speed. And finally, after this long journey, on July 1, 2004, Cassini enters orbit around Saturn, becoming the first spacecraft to settle long-term around the planet. Right from its arrival, the images are stunning. The rings appear in a new light, revealing structures even more complex than expected, with density waves, divisions invisible from Earth, and even interactions with certain moons. And then, on December 25, 2004, after several months spent in orbit, Cassini releases the Huygens probe, which then embarks on a unique journey in the history of space exploration. On January 14, 2005, the feat occurs. Huygens enters Titan's atmosphere and begins its descent. For nearly 2 hours, the probe traverses this dense and hazy atmosphere, analyzing its composition, measuring pressure, temperature, winds. Through the orange haze, Huygens reveals a breathtaking landscape. Rivers, valleys, dried lakes, a surface shaped by methane rains, sculpted by strangely familiar geological processes. Then, after a controlled descent, Huygens finally touches down on Titan's soil. It's a historic moment. Never before had a human-made object landed so far from Earth. The lander performs beyond expectations, transmitting valuable images and data for more than 90 minutes before its batteries run out. Huygens couldn't dig beneath the surface, but the collected clues open the way to a bold hypothesis. Titan might harbor somewhere a form of life adapted to this icy world. But another major discovery tempers these revelations. Titan doesn't have its own magnetic field. Unlike Earth, where the moving core generates a powerful magnetic shield protecting the atmosphere, Titan seems to be completely devoid of one. This means its core is probably not active or conductive enough to produce an internal dynamo, and this lack of protection has direct consequences. Instead of being isolated like Earth, Titan's atmosphere interacts directly with Saturn's magnetosphere. It is thus much more exposed to charged particles coming from the solar wind and the Saturnian magnetic field. And this raises an important nuance regarding the biological potential of this moon. Without a magnetic shield, the surface and atmosphere of this satellite are subjected to a constant bombardment of radiation. This phenomenon could have a significant impact on the development and stability of complex molecules, thus reducing the chances of life emerging on Titan. While Huygens provided these valuable data, Cassini continued its exploration, particularly on Saturn's rings, but also on Enceladus. Because it is in 2005 that we are fascinated to discover the geysers of water vapor erupting from its south pole. The probe passes through these plumes and analyzes their composition: liquid water, salts, methane, and even complex organic molecules. And Enceladus suddenly becomes one of the best candidates for the search for life in the solar system. Finally, after 13 years of mission, 294 orbits around Saturn, 453,000 images sent, Cassini is approaching the end of its journey. In 2017, its fuel tanks are almost empty. Cassini cannot be left abandoned. It could eventually crash into Titan or Enceladus and contaminate these potentially habitable worlds. For 6 months, Cassini performs 22 daring dives between Saturn and its rings, exploring a region that was never traversed before. The last images sent are astounding. Close-up views of the rings, gigantic storms in Saturn's atmosphere, unprecedented data on its magnetic field. Then, on September 15, 2017, more than 1 billion kilometers or 621 million miles from Earth, Cassini makes its final descent into Saturn's atmosphere. It plunges at full speed, transmitting its last fragments of data before the pressure and heat disintegrate it. And now, the exploration of the Saturnian system is far from over, because a new mission is being prepared: Dragonfly. This time, it's not an orbiter, but a truly autonomous drone capable of flying from one site to another on Titan, a first in the history of space exploration. Its objective is clear: to analyze Titan's surface to better understand its atmosphere, climate, and organic chemistry. Thanks to its dense atmosphere and low gravity, Titan is an ideal ground for a flying vehicle. Dragonfly will be able to cover great distances in a few hours and explore places inaccessible to a rover. It will start its mission in the dunes of Shangri-La, a vast desert whose structure resembles that of large terrestrial dune fields. Then it will fly to the Selk crater, a region suspected to have had several million years ago liquid water and complex chemical reactions. The challenge is significant. Titan is one of the most interesting places in the solar system to understand the emergence of prebiotic molecules. Dragonfly will attempt to answer a fundamental question. Does this moon harbor, or did it harbor in the past, conditions favorable to life? But the adventure will not begin immediately. The launch is scheduled for 2028, and Dragonfly will reach Titan in 2034. Once there, it will spend nearly 3 years exploring this strange moon, collecting unprecedented data and offering us a new perspective on one of the most mysterious places in the solar system. The story of Saturn and its moons is just beginning, and the future still holds many surprises, especially as, you can guess, Enceladus has managed to capture all our attention. Since the discovery of its gigantic water vapor geysers, scientists are convinced if one day we find a form of life elsewhere in the solar system, Enceladus is one of the best places to look. That's why several missions are currently being designed. The European Space Agency is considering a mission as part of the Voyage 2050 program, with a launch scheduled for the early 2040s and an arrival in the 2050s. NASA, for its part, is working on a project called Orbilander, scheduled for a launch in 2038 and an arrival on Enceladus in 2045. This mission would combine an orbital phase, followed by 2 years of surface exploration. But for the moment, these missions are not yet funded. The scientific interest is immense, but the technical and budgetary challenges remain numerous, and it will take several more decades before seeing a probe set foot on Enceladus. But through the exploration of Saturn and its moons, one thing becomes clear. The universe is a game of subtle balances. Look at Saturn's rings. These majestic structures in perpetual motion exist only thanks to the discrete presence of shepherd moons. Their gravity shapes the rings, keeps them in place, and prevents their dispersion. Without them, this spectacle would be nothing but chaos of particles scattered in space. Look at Enceladus. Under its thick ice crust, an ocean remains liquid thanks to the tidal forces exerted by Saturn. Without these constant deformations generating heat, the ocean would freeze, and with it, all possibilities for life. Look at Hyperion, that strange sponge-like moon. Its orbit, at the mercy of the gravitational disturbances of Titan, gives it a chaotic rotation, a permanent imbalance, yet surprisingly stable. An infinitesimal change in the forces acting on it, and its behavior could be totally different. Look at Titan. Its dense and mysterious atmosphere is the result of a complex chemical balance, a subtle game between the methane that evaporates and that which falls back as rain. The slightest disturbance, and this cycle could collapse, leaving the surface to dry up forever. Look at Saturn itself, so massive and yet so light that it could float on water. So fast that it becomes flattened at the poles, so far from the sun that its seasons last for decades, so turbulent that it is swept by supersonic winds, and yet its north pole harbors a meteorological structure of incredible stability, a perfect hexagon, frozen in the clouds for decades, as if the universe itself were trying to impose order in this celestial chaos. By scrutinizing these distant worlds, we do not just push the boundaries of knowledge. We learn to see our own world with a fresh perspective. Nothing is fixed, neither in space nor on Earth. If the story of Saturn teaches us anything, it's that balance is never static. It evolves, readjusts, reinvents itself.
Of the 3 stellar elements making up the system, Proxima Centauri is the shortest distance away at 4.2 light-years. However, While this triple system takes third place in terms of brightness in our starry sky, the Proxima star remains invisible to the naked eye. Let's get up close and personal with this fabulous trio and find out more. Alpha Centauri A and B form the main binary star. These two stars, which shine brightly like our Sun and bear a striking resemblance to it, are easy to spot. More traditional names have been attributed to these stars, depending on their location. Alpha Centauri A was christened Regal Centaurus, which to Arab astronomers means the foot of the centaur. As you can see, this star, the brightest in the Centaur constellation, marks the location of one leg of this mythological creature, half horse, half man. Its companion, Alpha Centauri B, was named Ptoleman, which translates as ostriches. The origin of this choice of name remains a mystery. Finally, Alpha Centauri C, the third star to be discovered, owes its common name Proxima Centauri to its proximity to our solar system, literally meaning the nearest centaur star in Latin. Let's take a look at how these three stars are organized. The initial duo is made up of two main sequence stars, one a G-type star like our Sun, of almost identical age, and the other a K-type star. This means that Alpha Centauri A bears a striking resemblance to our Sun, also categorized as G2 V-type. But, unlike our Sun, this star has around 10% more mass and a 22% larger radius. Its luminosity is also estimated to be almost 50% greater. The secondary star is of spectral type K1V, hence its slightly orange luminosity. Slightly smaller and cooler than its counterpart, Alpha Centauri B has a mass around 90% that of the Sun and a diameter around 14% smaller. Its luminosity, also lower, is estimated at 0.445 times that of the Sun, with an apparent magnitude of plus 1.35. Both stars have an orbital period, slightly eccentric, that spans almost 80 years. When the two stars are at their closest, 11.2 astronomical units separate them before they continue their course, moving a maximum of 35.6 astronomical units apart. To give you an idea of their maximum distance at aphelion, this is equivalent to the distance between the Sun and Pluto. But if you'd like to have the privilege of observing these two stars as they come closer together, see you in May 2035. As far as Proxima Centauri is concerned, it took a long time for it to be confirmed as part of the original system, and with good reason. This faintly luminous star follows a much more distant orbit than the sparkling duo, the period of its orbit having been estimated at around 600,000 years. Its trajectory takes it 10,000 times further away from its companion stars than the distance separating our Earth from the Sun. This is why it took scientists long periods of observation before concluding that this red dwarf is indeed gravitationally linked to the Sun. Astronomers believe that the red dwarf was caught up in the luminous duo as it passed by. Moreover, the proper motion of Alpha Centauri AB's center of mass is estimated to have a radial velocity of 22.4 kilometers per second, or 14 miles per second, in the direction of our Sun. This double system, dragging Proxima along with it, is therefore insidiously approaching us, and will occupy various positions in our night sky as it slowly advances, Brighter and brighter it will reach the Hydra constellation in 27,700 years' time, coming ever closer to our Sun at around 3 light-years. Its apparent magnitude should then reach its peak, rivaling that of Canopus, the second brightest star after Sirius. Because of its relative proximity to our solar system, Alpha Centauri is a fascinating object of study for scientists. In fact, it is the site of numerous discoveries, each more exciting than the last, including the detection of candidate or confirmed planets in the vicinity of these stars. The system's main duo, Alpha Centauri A and B, could well harbor this type of object, but no confirmation has yet been provided. This hypothesis is all the more plausible given that no brown dwarfs or gas giants have been detected in the vicinity of this stellar pair, reinforcing the idea that a rocky planet could have formed there, at least in theory. According to astrophysicists, there could be a 75% chance that a telluric planet, and a potentially habitable one at that, could exist in such a system. In 2021, a planet orbiting Alpha Centauri A was suspected. This exoplanet Candidate 1, estimated to be between the size of Neptune and half a Saturn, has an orbit approximately 1.1 astronomical units from the star, which it would cover in 1 year. As yet, this exoplanet has not been confirmed. Although the idea that it could be a background star has been dismissed, it could just as well be a dust disk, or even an artifact. Alpha Centauri B is no match for its close neighbor. It too seems to be accompanied by a planetary object. In October 2012, the sighting of a planet was announced by a Swiss astronomer. Named Alpha Centauri BB, this object, probably a telluric planet the same size as our Earth, is said to be experiencing terrible conditions. With an orbit very close to its star, and a period of revolution of just 3.2 days, one of its faces must be locked and constantly exposed to the 1,000 degrees Celsius or 1,800 degrees Fahrenheit of its sun. Since this statement, numerous studies have disputed the existence of this potential planet, including computer simulations. Although the actual existence of this candidate planet is in question, this challenge does not amount to a certainty either. In March 2015, another candidate planet was announced orbiting Alpha Centauri B, this time by a French astrophysicist. Slightly smaller in size than our Earth, this planet would also be too close to its star, although its orbit would last less than 20 days, and therefore be slightly wider. If the existence of this planet, named Alpha Centauri BC, were to be confirmed, it would unfortunately be unable to contain liquid water on its surface. Finally, it was with Proxima, the distant companion system, that not one, but 3 planets were detected for the first time. In August 2016, a team from the European Southern Observatory made this incredible announcement. Proxima Centauri B is the first confirmed exoplanet in this vast system. Probably telluric, this exoplanet has a mass at least equivalent to 1.3 Earth masses, and its radius could be 10% greater. What's more, its orbit, which it completes in 11.18 days, places it in the habitable zone of its host star, the system's sole red dwarf. Interesting, isn't it? 3 years later, in 2019, a second planet was detected in Proxima's vicinity. potentially a cold super-Earth or mini-Neptune, this exoplanet, named Proxima Centauri c, has a minimum mass of around 5.8 times that of Earth. It has an orbital period of just over 5 years, a long period that is of course attributed to its distance from its star, which is around 1.5 astronomical units. Although its existence was initially questioned, it was confirmed in 2020 by Hubble telescope recovery images dating back to 1995. Finally, an official announcement in February 2022 confirmed the existence of a third planet orbiting Proxima. This is Proxima Centauri d, a surprising exoplanet with one of the lightest masses for this type of object, only a quarter the mass of our Earth. Located just over 4 million kilometers or 2.5 million miles from its star, this exoplanet takes just 5 days to complete a full orbit. Although located in the hot zone, it is unfortunately not in its habitable zone. However, if its average temperature is estimated at 87 degrees Celsius or 190 degrees Fahrenheit, it could well be that these polar zones present more moderate, even welcoming temperatures. In short, this exoplanet could be home to large expanses of liquid water. In other words, oceans. Not all the observations made within this star system concern planetary-type objects. In 2017, a study carried out using the vast array of antennas at the Chile-based ALMA Observatory revealed that radiation from coal dust had been detected all around the Proxima star. According to the Spanish team, led by Guillem and Glada, the Proxima star is surrounded by cosmic dust rings. Composed essentially of particles of rock and ice that have not yet agglomerated to form a planetary object, these are not unlike the asteroid belts in our own system. Located beyond the orbit of the Proxima b planet, 2 dust-laden belts seem to encircle the star and its planet. The first appears to be 1 to 4 astronomical units away from the star, while the second, much less luminous, is around 30 astronomical units away. According to scientists, the inner ring has a temperature of minus 233 degrees Celsius or 450 degrees Fahrenheit, and a mass of 0.01 Earth masses. What's more, this ring proved to be a formidable marker for providing a potential indication of the detected exoplanet's inclination. Indeed, when this observation was made, only the exoplanet Proxima Centauri b had been detected. This prompted astronomers to take an even closer look at Proxima's surroundings, which were clearly home to more than just a single planet. In comparison, this belt would have properties equivalent to those of our Kuiper belt. According to these latest observations, Proxima is most likely surrounded by a complex planetary system, bearing a striking resemblance to our own solar system. This suggests that Proxima and its planet followed a similar process. The hypothesis that Proxima b has been captured no longer holds water. This exoplanet was indeed formed in this atypical system. Moreover, the discovery of 2 other planets in the following years has since supported this idea. However, the existence of these rings was soon called into question. The following year, a study echoing the findings of the Spanish team examined the 10 hours of observations already made on March 24, 2017. But this new study, unlike the first, was not based on the average brightness of the star during its observation period. And this second approach has radically changed the previous conclusion. It turns out that in reality, Proxima's luminosity increased by a factor of 1,000 in less than 10 seconds, before returning to its initial appearance in just under a minute. In other words, Proxima suffered an extremely powerful, particularly brief and confusing event. The reflection of red light on particles, simulating rings, was nothing more than an excess of luminosity due to a stellar eruption. Nevertheless, the phenomenon is not at all exceptional and is reminiscent of the well-known behavior of red dwarfs, renowned for their somewhat explosive temperament. Proxima Centauri is no exception to the rule, which for those looking for habitable planets precisely in this zone does not bode well. Let's get closer to these unexplored worlds and take a closer look. Let's start by getting to know Proxima c, better known as Gliese 551c. This is the most distant of the 3 planets detected near the Proxima star. Its detection was announced in April 2019 by an Italian team of astrophysicists led by Mario Damaso. It was while studying the radial velocity data of the Proxima star using the HARPS high-precision spectrograph at the Chile-based European Southern Observatory that they noticed movements. Although insignificant, these can only be explained by the presence of a significant object, namely a planet. But to confirm the existence of such an object, further studies were required. Scientists took a closer look at recovery images from the Hubble telescope, which dated back to 1995. But instead of focusing, as in the 1990s, on potential planets with orbital periods of no more than 1,000 Earth days, they widened their search perimeter. After reanalyzing a wealth of astronomical data collected by Hubble, the researchers confirmed that there were indeed signs of an exoplanet in the vicinity of Proxima. As a result, the existence of Proxima c was confirmed in 2020, as it has a long orbital period. Images of Proxima c were even unveiled to the general public, thanks to the Sphere instrument on the European Southern Observatory's Very Large Telescope. Proxima c is therefore the first exoplanet, and the closest to our Earth, to have been immortalized by a lens. Together, these 3 studies have provided a wealth of information about this exoplanet. We now know that its mass is 7 times that of Earth, placing it in the category of super-Earths and mini-Neptunes. It takes more than 5 years to complete a full orbit, lasting exactly 1,928 days. This duration is of course related to its distance from the star Proxima, of which it is about 1.5 astronomical units away, i.e., almost 220 million kilometers, or 135 million miles. Given this configuration, could Proxima c harbor any form of life? This is highly unlikely, as life evolves well beyond the snow line, with the star's habitability zone lying between 0.05 and 0.1 astronomical units. With its equilibrium temperature estimated at just 39 kelvins, or around minus 234 degrees Celsius, it's likely that water can only exist there in its frozen form. Indeed, if Proxima c isn't a Lilliputian version of the famous gas giant Neptune, and indeed turns out to be a super-Earth, it may be covered by a thick mantle of ice. Let's continue our journey towards the star Proxima. The second planet we come across is Proxima b, also known as Gliese 551b. As mentioned earlier, this is the very first exoplanet discovered orbiting the star Proxima. As you can see, in terms of size, it's much larger, probably twice the size of its neighbor. Closer to its host star, at just over 7 million kilometers or 4 million miles, it orbits in 11.2 Earth days, receiving around 79% of the heat our Earth receives from the Sun. If it weren't for its sandy hues, it could almost be mistaken for our beautiful blue planet, couldn't it? Indeed, Proxima b is quite similar to our Earth in terms of mass, estimated to be at least 1.27 times that of Earth. Likewise, its radius appears slightly larger. But above all, because of its position, this exoplanet evolves in the habitable zone of the red dwarf, which grants it mild temperatures, particularly suited to the presence of liquid water on its surface. While the distance separating it from its host star gives it a temperate climate, let's not forget that the latter is a red dwarf, a star much colder than our Sun and up to 1,000 times less luminous. Proxima b is therefore much closer to its life vector than we are to the Sun, the distance being less than that separating the latter from Mercury. And this is not without consequences. Proxima b is strongly subject to the tidal forces of its parent star, which unfortunately synchronizes its period of rotation around its own axis with that of its orbit around the star. In other words, this exoplanet is tidally locked, probably exposing the same face to its host star at all times. But once again, this is only a hypothesis. Indeed, depending on the resonance with which it interacts with its local sun, the consequences might not be so catastrophic. In the case of a one-to-one resonance, the most pessimistic hypothesis, one of its faces would be eternally exposed to the star, with temperatures never falling below 40 degrees Celsius or 104 degrees Fahrenheit. The other side, meanwhile, would be plunged into endless icy darkness. On the other hand, if it were a 3-to-2 resonance, Proxima b could prove much more hospitable, although conditions would be far from those we enjoy on Earth. This means that the planet would be able to make 3 rotations on its own axis over a period of 2 years. Taking into account its orbit, which lasts 11.2 Earth days, this means that a day on Proxima b would stretch over 7.5 of our days, with relatively significant temperature variations. While this hypothesis remains conceivable, the presence of an atmosphere and a hydrosphere, both indispensable to the existence of any form of life, may generate other problems. Sometimes cold, sometimes hot, these elements generate irregular heating and thus convective movements, manifested by winds and ocean currents. Various models suggest that if Proxima b is covered by a gigantic ocean, the heat from the sunlit hemisphere could spread widely over the cold hemisphere along the equator. Different simulations based on more or less massive atmospheres put forward other ideas. In the case of a relatively thin atmosphere, heat distribution could be very uneven across the planet's surface. Conversely, a much more massive atmosphere, allowing maximum concentration of water vapor, could lead to more even heating, which would have an unexpected consequence. Proxima b would be largely ice-free, offering much more hospitable temperatures for the development of life. Now let's discover the third planet in this system. This is Proxima d, also called Gliese 551d by scientists. It lies just 4 million kilometers or 2.5 million miles from its host star, and is therefore located in the hot zone, slightly below the limit of the habitable region. What makes it special? It is one of the lightest exoplanets ever detected using the radial velocity technique, with an estimated mass a quarter that of our Earth. Its discovery, albeit recent, has proved to be a technical feat. With such a tiny mass, the gravitational effect it produces on its host star is extremely weak. As a reminder, the radial velocity technique involves measuring the tiny movements of a star caused by the gravitational attraction of an orbiting planet. In this case, it enables us to observe with incredible precision oscillations of Proxima Centauri measured back and forth at just 1.4 kilometers per hour or 1 mile per hour. It's easy to see why this type of object is so difficult to detect. Lasting 5 days, these small variations indicated the time needed for the planet to make a complete orbit around its star. It took the scientists almost 100 nights of observation to reach this conclusion, as the signal emitted by the star was particularly weak. But their patience was rewarded, as this discovery paved the way for many others. Because of its location in the system, Proxima d is probably a rocky planet. Its singularly low mass certainly prevents it from trapping gas in the same way as gas giants such as Jupiter, Saturn, or Neptune. It undeniably resembles a devastated Earth. Scorched in places by a constant average surface temperature reaching 87 degrees Celsius or 189 degrees Fahrenheit, while the polar regions experience more moderate circumstances. If this planet isn't the most hospitable, its discovery is nonetheless of the utmost importance. It suggests that all stars have their own multiplanetary systems. Thanks to the espresso spectrograph, it's a safe bet that many other planets previously invisible to the instruments will finally be unearthed. Another high-precision instrument will soon be pointed in the direction of Proxima c. Called Ristretto, it should enable us to observe Proxima's light reflected by the exoplanet. When this new instrument is in action, it will enable scientists to deepen their observations, and why not detect the hypothetical atmosphere or the possible presence of water? If the existence of these elements were to be confirmed on one of these planets, and on Proxima b in particular, it would be fantastic news. Proxima, as the closest star to us, is therefore an ideal target for scientists hoping one day to find any trace of life beyond our solar system. This is especially true now that Proxima b has been detected and located within the habitable zone of this red dwarf. However, there is much debate among scientists about the prospects of life near this category of stars, namely cool, low-mass M-type stars. These are among the most widespread in our galaxy, with a high frequency of exoplanets roughly comparable to Earth, and with equilibrium temperatures suitable for the presence of liquid water on their surfaces. However, red dwarfs are renowned for their unpredictable behavior, which has a particularly strong impact on their immediate environment. Indeed, these stars, although small, are active and unstable, with the usual stellar eruptions. As you may have guessed, Proxima is no exception to this rule. As part of a study of Proxima, covering some 40 hours of observation between April and July 2019, a team of researchers from the University of Colorado recorded a most spectacular stellar flare. It was recorded on the 1st of May, 2019, by 5 of the 9 instruments pointed in its direction, including the Hubble Space Telescope, the TESS satellite, and the high-performance ALMA terrestrial radio telescope, which alone brought together more than 60 dishes. According to the study, the star became 14,000 times brighter in ultraviolet wavelengths in the space of a few seconds. Scientists were amazed by the exceptional power of this burst of radiation. To give you an idea of the scale of the phenomenon observed, it turned out to be almost 100 times more powerful than the strongest flares ever seen on our sun's surface. Although it didn't produce much visible light, this explosion was unusually intense in terms of ultraviolet and radio radiation. Lasting just 7 seconds, it therefore produced millimeter wave signals. For scientists, this was a momentous observation. It confirmed that stars are capable of blazing in the millimeter range. This new type of signal is a godsend for researchers trying to learn more about how stars produce their flares. All the more so, as during the hours Proxima was under observation, astrophysicists noted a multitude of other flares on the star's surface. Not only does this mean that this type of flare cannot be described as rare, but more importantly, that such events are probably a daily occurrence. In fact, another team of astronomers had already announced in 2017 that they had captured a stellar eruption on Proxima's surface. Phenomenally powerful, it is likely to have been capable of destroying any Earth-like life present in a certain area. For the planets orbiting Proxima, this finding is far from optimistic about the presence of any form of life, at least as we know it. For if there were life on Proxima Centauri's nearest planet, Proxima b, it would have to be very different from anything on Earth. If not, any living organism that has experienced this stellar eruption has inevitably had a rough time of it. Planets in the vicinity of this star, which experience this kind of cataclysm on an almost daily basis, may see their potential atmosphere dwindle over time, if they even have one at all. Stripped of this protective bubble, these exoplanets would no longer be capable of harboring any kind of life at all, as they would be fatally exposed to deadly solar storms. But once again, this is nothing more than speculation. The high-energy radiation produced by this red dwarf has yet to concretely reveal its impact on the immediate environment. Further observations will be needed to shed light on an exciting subject: planetary habitability alongside the Proxima star. Apart from the problems caused by these stellar eruptions, there's another parameter, and not the least important one, to consider for researchers of potentially habitable planets. This is the star's lifespan. Assuming our humanity lasts several million or billion years, it would be a shame to have chosen as our promised land a planet evolving around the corpse of a star, wouldn't it? By the time our sun, in 1 billion years' time, begins its long transformation into a red giant, then undergoes a collapse followed by slow cooling, what will become of Proxima Centauri? A red dwarf is not to be confused with a low-mass star at the end of its life, having once shone brightly before slowly fading away. The latter has not undergone the same evolutionary process. A yellow dwarf at the end of its life generates helium fusion, gradually transforming into a red giant. Then, when this fuel is exhausted, it becomes an insignificant white dwarf, losing more and more of its luminosity until it glows red, before dying out forever and turning into a hypothetical black dwarf. While yellow dwarfs like our Sun have an estimated lifespan of 10 billion years, Proxima has a different destiny. Initially too small and hot to become luminous like yellow dwarfs, this star consumes its hydrogen extremely slowly. It belongs to the type of star with a convective interior. This means that energy flows from the core to the outer layers through the motions of the glowing plasma. Yellow stars, on the other hand, have a radiative interior, conducting their energy outwards from the core, using a form of electromagnetic waves, thus rapidly stripping it of its fuel. Proxima, like all red dwarfs, has a particularly long lifespan, estimated at between a few tens and 1,000 billion years, or even more. By the time this red dwarf has exhausted all its resources and become a white dwarf in its turn, without passing through the red giant stage, it should gain considerably in luminosity. But before it reaches this stage, heating up its planetary system, a few billion years will have passed. Now you understand why this modest star is the focus of so much scientific attention. If other planets were to be discovered in its habitable zone, which is not excluded, the chances of conquering a new world would be greatly multiplied. As astrophysicists search for potential habitable extrasolar planets, they are equally on the lookout for hypothetical traces of extraterrestrial life. The SETI program for the Search for Extraterrestrial Intelligence, created in the 1960s, is proof of this. On August 15, 1977, this collaborative program caused quite a stir. Jerry Emmon, an astrophysicist from the state of Ohio, recorded a particularly strong signal with the Big Ear radio telescope, seemingly coming from a group of stars in the Sagittarius constellation. The signal astonished him so much that after printing the trace of this radio frequency, he circled it with a red line, then froze his amazement in the margin with an annotation, "Wow." This mysterious 72-second signal, emitted on the 1.42 GHz frequency, then became the famous signal "Wow." This strange message from the cosmos received by the Earth. However, listening to this radio wave was no accident. Indeed, before scientists set out to listen to the sky in the hope of detecting potential ET signals, they calibrated their equipment. To give themselves every chance of one day listening for such a signal, their radio telescope was set to a precise wavelength, known as the 21-centimeter ray. This choice was based on an obvious deduction. The electromagnetic radiation produced at this wavelength corresponds to that which best penetrates hydrogen. Hydrogen is the most abundant element in the cosmos. The recording of this signal came as a great and unexpected surprise, generating doubt. A more down-to-earth explanation was sought. Due to an international agreement, the frequency used is reserved exclusively for this program, precisely to avoid any terrestrial interference. What's more, no known natural phenomenon can emit such a signal. The hypothesis that a pulsar is at the origin of this signal has also been studied, with no concordant results. Even the possibility of a computer error in the system was considered, but dismissed for lack of evidence or occurrence. Finally, the passage of two comets through the radio telescope's listening field has been the subject of debate ever since, their existence having only been proven much later, in 2006 and 2008. For many scientists, however, the latter explanation does not seem credible at all, as various pieces of evidence support it. Since then, a complementary project, Breakthrough Listen, was launched in 2015. Its aim is to focus on unexplored radio frequencies identical to those commonly used on Earth for all kinds of communications. In April and May 2019, radio signals were intercepted from the vicinity of the Proxima Centauri star. The source of these signals has been named BLC-1 for Breakthrough Listen Candidate 1. While astronomers on this project regularly spot unusual radio wave bursts, these are usually explained by human interference. But this latest one, detected 5 times during some 30 hours of observation, has passed various tests, greatly arousing their curiosity. All the more so as it occupies a particularly narrow band of the radio spectrum, the only source known to date capable of transmitting at 982 MHz being human. For scientists, the task now is to sort things out. Is it really an extraterrestrial technosignature, as many exobiologists and science fiction novelists dream? Or is it yet another case of interference from Earth? But researchers aren't content to just listen to the universe. Over the past few decades, several messages have been sent to specific regions of space, addressed to a potential extraterrestrial civilization. While most messages have been transmitted by radio, some in the form of images encrypted in binary code, others have been composed of drawings, like the one attached to the Pioneer 10 probe. An even more sophisticated message, 2 golden discs containing images of the Earth, musical data or ambient sounds of our planet traveled through space on the Voyager 1 and 2 probes. These messages, like bottles thrown into the sea, should they one day encounter a form of life, are nevertheless no guarantee of a future dialogue between civilizations. Who is to say that a potential life form beyond our planet would be able to intercept these messages? After all, these supposed extraterrestrials may not perceive their environment as we do. Their language could have evolved in a telepathic mode, rendering sight and hearing obsolete. Nevertheless, as long as the contrary has not been formally demonstrated, the hope of finding a trace of life in the Alpha Proxima system, or at the very least a habitable planet, why not one that can be terraformed, is still alive and well. For the record, let's not forget that our own system could yet reveal some of its secrets. Astrophysicists suggest that a 9th planet, as yet unobserved, may exist in the outer reaches of our solar system, somewhere in the Kuiper Belt. If the existence of this celestial body were to be confirmed, which could well happen in the very near future, it could explain the unusual motions observed with certain objects evolving beyond Pluto's orbit. So, with our eyes riveted on the promising Alpha Centauri system in search of exoplanets, even if it is a fantasy, the idea is not absurd. Especially as techniques for detecting distant objects, even those of low mass, are becoming increasingly precise. But while we await major revelations, such as, why not, the discovery of an exoplanet similar in every way to our Earth, let's take a look at what life might look like on the planets we've observed. As we've seen, Proxima d is far too close to its host star to offer us a comfortable place in the Sun. Its telluric appearance hides an inferno of fire and ice, as the planet is trapped in a synchronous rotation. On the one hand, its sky is eternally ablaze with the glow of the red dwarf it borders, its atmosphere a toxic mixture of gases. Violent, fiery winds plow its rocky surface, resembling a desert of molten glass. Its night side, also desolate, is an ice abyss, plunged forever into cosmic darkness. Even if any trace of life could ever have formed on this planet, even if only in the form of bacteria, at present it can only be completely annihilated, at least on its day side. As for Proxima c, the most distant of the three planets orbiting Proxima, the picture is not much brighter. Its status is still unclear. Is it a gas giant resembling a mini Neptune, or a super-Earth? In either case, it's an extremely cold world, far too far from the habitable zone of its host star. However, if it turns out to be a super-Earth, the idea that it could harbor life in a form other than the one we know may not be so far-fetched. Imagine that this planet contains large quantities of water. In that case, it could be entirely covered by oceans that are completely frozen, or at least several kilometers or miles deep. Unwelcoming, isn't it? Now imagine what its seabed might look like. Although completely deprived of the weak glow emitted by the local sun, they could nevertheless experience temperatures more favorable to the development of a certain biosphere. The regular activity of submarine volcanoes could enable this singular environment to keep simple multicellular organisms alive in such ocean depths. Of course, this is all speculation, not to say daydreaming. Let's now turn our attention to the most attractive of these three planets, Proxima b, which has enthusiasts enthralled. While it does indeed lie in the temperate zone surrounding the red dwarf, its proximity makes it particularly vulnerable. As it too is locked in by tidal forces, this planet probably consists of two distinct worlds, a day side and a night side. In theory, its overall temperature allows for the presence of liquid water on its surface, the supreme condition for all life. But does it still have an atmosphere, which is also essential? If so, it would be plausible for temperatures to be in the region of -30 degrees Celsius or -22 degrees Fahrenheit on the shady side, and 30 degrees Celsius or 86 degrees Fahrenheit on the light side. Unfortunately, if an atmosphere is or was present on the surface of Proxima b, some scientists agree that its existence is highly compromised. Remember the activity described earlier of Proxima Centauri, its recurring tantrums concretized by intense ionizing rays and repeated solar storms. Because of its short distance from its red dwarf, this planet is particularly exposed to its X-rays and ultraviolet rays. According to researchers, the latter could be up to 100 times more powerful than those we receive from the Sun. Despite this, the idea that Proxima b still has an atmosphere has not been completely ruled out. Numerous simulations of planetary worlds evolving in systems similar to Proxima Centauri show that the majority of planets are either completely covered by a vast, thick, icy ocean or have become barren rocks. Far rarer planetary objects comparable to our Earth, however, exist in orbit around old red dwarfs that have become less active. In the case of Proxima b, this relatively massive super-Earth appears to have absorbed large quantities of water particles and surrounding gas in its early stages. If this hypothesis is confirmed, a particularly dense atmosphere of oxygen and nitrogen could envelop it, masking a mysterious oceanic world. The existence of this atmosphere, potentially 10 times more abundant than that which protects our Earth and of oceans several kilometers deep, cannot be ruled out. Despite the explosive nature of its neighboring star, Proxima b has not yet been completely stripped. Some scientists even consider that it may have retained a sufficient atmosphere and a sizable hydrosphere. The planet's large size is therefore a definitive advantage, especially since the presence of a magnetic field is highly probable. A planet of this size, though tidally locked to its star, may not yet have come to a complete stop in its rotation. Its core could still be hot and mobile for a long time, generating a substantial magnetic field, perhaps even greater than that of our Earth. Now imagine that these three factors were combined: a dense atmosphere, a considerable hydrosphere, and a strong magnetic field. They would provide the conditions necessary for the survival of many forms of life, protecting them to a large extent from the harmful and devastating radiation of the Proxima star. Although this world, if it really exists, is plausibly an essentially aquatic one, failing to be truly hospitable, it remains no less captivating. In a recent study of 17 exoplanets, NASA's Dr. Lene Quick and her colleagues shed some light on their habitability. According to their findings, Proxima b, like the other extraterrestrial worlds studied, may unfortunately not be as hospitable as hoped. On the one hand, it seems less dense than our Earth, suggesting that it would be composed essentially of ice and water rather than rock. The surface temperature, a priori colder than first estimated, implies that this oceanic planet would be completely covered by a mantle of ice. The thickness of this mantle is estimated at nearly 58 meters or 190 feet. On the other hand, based on the intensity of geysers on Europa, one of Jupiter's moons, they calculated that Proxima b could have an extremely high rate of geyser activity. This appears to be hundreds or even thousands of times greater. Cryovolcanic eruptions in the deep ocean would expel considerable plumes of steam and ice particles far from the surface. Proxima b would in fact be dotted with abundant geysers cutting through its ice mantle, especially as the latter appears to be much thinner than on many similar objects. All these assumptions are based on observations made using the latest technology and on scientists' current knowledge. In the near future, as science continues to advance, these assumptions may be called into question. As you may have noticed, what seems to be true one day may turn out to be false the next. So who knows? Perhaps a future study will bring other conclusions, perhaps more favorable to a long-awaited discovery. With this in mind, scientists have long been considering sending out scouts in the form of onboard technologies. But what are their practicalities? Assuming that our current technology would allow such an expedition, how long would it take a spacecraft today to reach Proxima, the star that is our solar system's closest neighbor? Unfortunately, far too long. Currently, the fastest space probe ever designed is NASA's Parker Solar Probe. Launched in August 2018 to study the outer atmospheric layers of our Sun, it has been setting record after record ever since. Its latest came on September 27, 2023, when it reached a record speed of 635,000 kilometers per hour, or 395,000 miles per hour. This is 15 times faster than the fastest manned spacecraft. If we could travel at the same speed, it would still take us almost 7,300 years to reach Proxima Centauri. Assuming we could travel at the speed of light, this journey would be reduced to 4.2 years. To date, only 2 probes have crossed the boundary of our solar system. Launched on September 5, 1977, the Voyager 1 and 2 probes are the first man-made objects to travel through interstellar space. Voyager 1 was the first to cross this boundary in 2012, 35 years after its launch. It has enabled scientists to learn more about our Sun, its interactions with particles and magnetic fields outside our heliosphere. These observations have provided key information for future missions. As for the Pioneer 10 and 11 probes and the New Horizons probe, launched respectively in 1972 and 2006, while they have reached the limits of our solar system, the former are no longer in a position to emit anything. New Horizons, whose primary mission was to fly over the planetary objects of our solar system, will never be able to catch up with the Voyager probes. As you can see, space travel to the Proxima star is still a fiction. NASA's ambition was to develop a technology that would enable a probe to travel at a considerable speed, around 10% of the speed of light, in order to complete the long journey in just 44 years. At least that's what the team at NASA's Jet Propulsion Laboratory was aiming for in 2016, with the goal of sending a probe to explore Proxima b by 2069. To give you a benchmark, it would take Voyager 1 around 80,000 years, assuming it ran into no obstacles, to get close to Proxima Centauri, its cruising speed being 16 kilometers per second or 10 miles per second. NASA is therefore looking into ways of reaching Proxima in the shortest possible time, especially since if this feat were to be achieved, it would still be more than 4 years before any recorded data would reach us on Earth. A major technological breakthrough is therefore essential if a mission of this scale is to succeed. A combustion engine powered by a nuclear fission reaction could achieve this. Unfortunately, according to scientific estimates, it would take 1,000 years. Engineering using pulsed nuclear propulsion, still theoretical, would enable this crossing to be made in a century, but without guaranteeing the safest possible journey, as its nuclear payload represents a considerable risk. According to astrophysicist Michael Gillon, nuclear fusion, provided that a nuclear fusion engine is mastered, which is still a long way off, would shorten the journey time to just 36 years. Faced with this more than ambitious project, NASA has finally associated its Innovative Advanced Concepts Program, or NIAC, with a private initiative called Breakthrough Starshot. Launched in 2016, Breakthrough Starshot is a commercial research and engineering project estimated to cost $100 million. Many visionaries who also dream of conquering space have taken part in this project, which aims to explore deep space and potentially discover other habitable planets. Their primary objective is to encourage technological innovation by bringing together eminent scientists to make a voyage to Proxima Centauri possible in a few decades' time. Research teams are hard at work on advanced technologies that will ultimately benefit humanity. These should revolutionize our understanding of the universe and offer future generations the opportunity to finally explore other interstellar worlds aboard spaceships. One of the main challenges facing researchers is to develop a propulsion system capable of propelling a spacecraft at a speed equivalent to 20% of the speed of light. To achieve this ambitious goal, researchers are currently developing 3 key programs. The first is the design of a miniaturized spacecraft known as starships. These nanoprobes, equipped with computer chips and a whole range of communication systems, must withstand the extreme conditions they will be confronted with. The second is the development of a propulsion system based on lightweight sails, the light sail system. Based on optical technology, these sails are made of a material only a few hundred atoms thick. Last but not least, the development of a ground infrastructure to supply, via a laser system, the energy required by this light sail to propel and steer the starships towards its destination, Alpha Centauri, and more specifically, the star Proxima and its planetary system. To multiply the chances of succeeding in this crazy gamble, 1,000 star-chipped ships, each weighing no more than a gram. Thanks to the laser's unrivaled power of 100 gigawatts, these nanovessels would then be able to reach a speed of around 20% of that of light. Like a swarm, these extraordinarily autonomous probes will progress with perfect synchronization to form a mesh network covering an area of around 100,000 kilometers or 62,000 miles in diameter. This process should ensure that a minimum number of probes, despite a high loss rate or poorly controlled direction, reach the coveted target of Proxima. The scientists' efforts have just been rewarded, with NASA selecting their concept for Phase 1 development under their NIAC, or Innovative Advanced Concepts program, at the start of 2024. The only solution at present, therefore, is to reverse the rocket. Instead of the rocket expelling a material to be used as fuel, it is necessary to launch something onto the vessel that will enable it to move forward. In this case, like the wind blowing over the sail of a boat, photons would strike the photovoil of each of these nanoprobes. Although scientists have made tremendous strides, such a mission is unlikely to see the light of day before 2075. The concept, though very promising, must overcome enormous difficulties. These include the robustness of the sail. Will it be able to withstand the heat generated by the laser beam? Or to sudden accelerations? Or the gas and dust it might encounter? On the other hand, control from Earth will be impossible. Scientists therefore have to develop genuine robotic probes. The swarm, as they are called, must be perfectly autonomous. Finally, the manufacture of this high-tech swarm and the construction of a terrestrial laser system, not to mention the research work, represent a staggering budgetary outlay. Even if each of these probes on a gram scale does not generate exorbitant manufacturing costs, the project as a whole is the most ambitious ever envisaged. In the silent immensity of space, the Alpha Centauri system shines like a distant promise, and like a lighthouse attracts our boldest dreams. Imagine a world where the stars are no longer out of reach, where the secrets of the universe are revealed to us on fabulous interstellar journeys. Proxima b, the exoplanet that's raising our wildest hopes, could hold the key to our deepest questions. Is it the cradle of extraterrestrial life? Do its oceans conceal strange forms of life? Is it a potential future home for mankind? or on the contrary, a place of nameless desolation, begging to be fled. The technological advances under development, these robotic probes that could one day split the vacuum of space, are not mere tools. They are messengers of our curiosity, probably the pioneers of a new era. Each of their discoveries, beyond helping us to take another step towards understanding our place in this great whole, will be a formidable legacy for our future generations. More than a scientific feat, the project to spin off Proxima using these solar minnesons is a veritable symbol. Alpha Centauri, and the Proxima system in particular, may still seem a long way off today, but every step we take brings us closer to the moment when we can say that we are travelers among the stars. And who knows, perhaps in just over a century's time, the first images of Proxima b will reach us.